Now that we've looked at strong inference, it's time to talk about an important set of terminology that goes with strong inference, which is how frequentist statisticians categorize error. So when we talked about strong inference, you saw that we didn't actually have any data in the last lecture. You can break up all the different possible outcomes of a strong inference research project without having to actually collect any data. And it turns out there are two different ways that we could run into erroneous results when we use this process. So when we're talking about this, we're not talking about systematic error, like having a non-representative sample from the population or having our research instrument break or something like that, so we have bad data. We're not talking about bad data, we're talking about bad luck. So it's a noisy world, and so we might have this population which is sort of bluish green, and I apologize for red-green colorblind people, but there are these maybe these are the only 4 reddish objects in this whole population, but by bad luck we got them. And then we might say that actually we believe that the typical color for the population is sort of a pinkish color. We would be wrong. So we have to think about the consequences of what something like that would be. So the first kind of error, the error that frequentist statisticians most want to avoid, is called type 1 error. It's a Roman numeral 1 there. And that is when we see something that isn't there. So in the real world, there's no actual relationship between the variables that you think are related to each other. So your research hypothesis has stated that there's a relationship between variable A and variable B, and you collect the data in your sample and you find that relationship between variable A and variable B in your sample. But it turns out, maybe through more extensive research or having something else happen that shows that you're wrong, that in the real world, that relationship's not actually there. So by mistake, you reject the null hypothesis, and by error, therefore, you call the research hypothesis supported. It's a type 1 error. The other kind of error, shockingly, is called type 2 error. And that is when you miss a relationship that is there. So your research hypothesis has stated that there is a relationship between variables A and variables B, but you collect the data and you fail to find that relationship. You have to reject the research hypothesis, and you find that the null hypothesis is supported. And so later on, further research might show that there actually is a relationship. Typically, frequentist statistics consider this to be a less severe type of error, because if you miss something that is there, that means that it's probably not that strong a signal, and so it might not have as big consequences as seeing something that's not there. And a lot of times that's because a type 1 error leads you to change the status quo, and a type 2 error leads you to keep the status quo. And if the status quo was already doing well enough that you could afford to do statistical analyses, then it couldn't be totally awful. So here is a table. So over here, this is what our data lead us to believe. And then over here, this is what's actually true. So if the null hypothesis is actually true, if there's no relationship between the two variables, and we reject that, we find a relationship in our data, we commit a type 1 error. If we find no relationship in our data, and we reject the research hypothesis, then we have succeeded. Likewise, if the research hypothesis was actually true, and our data lead us to reject the null hypothesis, then we've succeeded. If the research hypothesis is actually true, there is a relationship between A and B, but we fail to find that relationship in our data, we commit a type 2 error. So these are the 4 possible outcomes from a strong inference type approach. So to try and make this a little bit more believable, I'll use an example from Star Wars. So the first thing we have to think about when we're doing a hypothetical like this is what variables to use. So I'm going to list here 3 possible discrete variables. One variable that's discrete is Yoda in the film? It's a yes or no, right? Another discrete variable will be, what is the main habitat in the main planet. Is it an ice planet? Is it a desert planet? Is it a jungle planet? And another discrete variable would be what decade was it produced in? Was it in the 70s, 80s, 90s, aughts, or teens? You could also think of some continuous variables. The film's Rotten Tomatoes score, how much money the film made, and how many Jedi there are in the film. So you can see that the unit of observation here is the film. So my hypothesis that I'm going to consider right now is that 2-minute Jedi are bad for the film. So here's the research hypothesis. Cramming Jedi into a script is a symptom of bad writing. Therefore, the more Jedi in a film, the worse its Rotten Tomatoes score will be. So if we reverse the cause and effect relationship versus the prediction in this example from the ones previously about studying the grades and the weights of the elephants in the photographs. So our prediction is that there will be a negative correlation between a film's Rotten Tomatoes score and the number of Jedi rolls that it has. They're both continuous variables, so the appropriate way to see if there's an association with them is with a correlation test. And if Jedi aren't the problem, that's our null hypothesis. The number of Jedi in a film has no impact on its Rotten Tomatoes score. And here I've tried to break up the null situation into a hypothesis and a prediction. So the prediction is that the correlation between a film's Rotten Tomatoes score and the number of Jedi rolls that it has will be 0 or greater. So typically when we do a null hypothesis, we blend these two things together, but you can split them into hypothesis and predictions if you want to be totally perfect about your distinctions between hypotheses and predictions, which everyone should be, but no one is. Okay, so now that we've set up our hypotheses and predictions, we can actually consider what the errors might be that we can consider. So the worst kind of mistake we can make would be a type 1 error. So that would mean there really is no relationship between Jedi and tomato meter reading, but my data make me think there is one. In that case, I might take unnecessary steps to remove Jedi, going back and altering the films and things like that, and that would just be a lot of effort for no result. So that would be why it's the worst kind of mistake to make. Type 2 errors are still pretty bad. If you commit a type 2 error, that means there really is a relationship between the Jedi and tomato meter rating, but I fail to detect it with my data. In that case, I might ignore the Jedi when removing them, and the film will be best. Since the films have already made tons and tons and tons of money, maybe we could have made a little bit more money, but it's not like the end of the world if we have a few extra Jedi knocking around.